Hi, so for our gas laws, normally you would be whiteboarding some pictures, and these are called particle diagrams. So if you want to do this with me, and I hope you will, take out a piece of paper and a pencil and draw away. We're going to start with a pressure of 10 atmospheres and a volume of 2 liters. Okay, notice these are gases, so these little lines mean they're moving. If you drew a larger line, it would mean they were moving faster. So now I want you to draw another box, and I want you to change the volume to 1 liter and show me what that would look like. Put your same number of particles, because we have the same moles, that's kept constant, and our temperature is kept constant. So what would that mean for the arrows? Okay, so pause your video now and draw away. Let's see what you get. Okay, so hopefully you drew your volume at 1 liter, which is half the volume. Notice my arrows are the same size because we have the same temperature. They have the same kinetic energy. They're moving at the same speed. What would this do to my pressure? Would my pressure increase or decrease? Well, we have the same number of particles colliding against the walls, but here they have less distance to travel, so they'll be colliding more. And since this is a directly inverse relationship, if the volume goes down by half, my pressure is going to go up times 2. So my pressure would equal 20 atmospheres. Now that's really simple to do in your head, but we have a formula here. And if you notice, I put in my 10 atmospheres times my 2 liters is going to now equal 20 atmospheres times my 1 liter, and that is going to be 20 equals 20. So they are the same. My initial volume and pressure equal my second condition. Although my variables have changed, the product of them is the same. So again, this looks simple in your head, but they're going to get complicated, and what I need you to do is to do some algebra. So here we were solving, we were solving question mark for our pressure 2. Okay, so what you would do is you would square off, I'm solving for my pressure 2, that was my question mark to start, and you need to get that variable alone. How do you get that variable alone? Well, I have to get rid of my volume here, so I would divide by volume, and now my equation's not equal. How do I keep it equal? It's a balance, right? If I take away something on this side, I have to take away something on this side. Now my volume 2 cancels out, and I have pressure 1, volume 1 divided by volume 2 equals pressure 2. This is much easier than plugging in your numbers first and rearranging. So rearrange your formula and then plug it in. So my next question, if my volume decreases by half, my pressure goes up times 3. If my volume goes down a third, what does my pressure do? Well, we already said if my volume goes down, my pressure goes up, and it's times 3. Okay, so completely inverse. It's Boyle's law. It's our inverse relationship. Okay, so now we're going to look at Charles' law, which is volume and temperature. Okay, so here I have a temperature of 100 Kelvin, and my volume is 2 liters. I want you to tell me what happens if I increase my temperature to 200 K. What happens to my volume 2? This is temperature 2, volume 2. So pause the video and draw. This is a piston and it's movable. Why? Because our pressure needs to stay constant and our volume is changing. Okay, so pause your video and draw that and see what you have. Okay, so this is a direct relationship, but it's similar to this in that if my temperature doubles, my volume is going to double. Maybe you guessed that, maybe not, but I'm telling you that. And what happened in my picture? Well, my volume doubled, and notice my arrows are longer because the kinetic energy is more. Temperature is average kinetic energy. Think about this. If I had a bunch of jumping beans in here and they were pounding on this to where they kept it this constant, and then I made those jumping beans go even faster, they would be pushing up this, increasing the volume. Okay, so what did we solve for? We solved for our volume 2. That's right here. How would I rearrange that equation if it wasn't this simple? Well, I would have to get rid of my volume 2, so I divide this side by volume 2. Oh, wait, hold on. I'm solving for volume 2. I need to get volume 2 alone. So what do I have to do? I have to multiply everything by temperature 2, which means I have to do it to this side as well. Now, my temperature 2 gets crossed out here, and I have T2 V1 over T1 equals my volume 2. I've got my volume 2 alone. That's what I'm solving for. And now I would plug in my variables. Okay, so I'm going to show you a couple things how to choose which formula to use. Really easy using a special chart. But once you figure out your formula, you're going to have to rearrange it algebraically. So go back and use these videos to show you how to do that. So just to reiterate, this is a direct relationship. When my temperature doubles, my volume doubles. And if you put it in your formula mathematically, you would see that's exactly what happens. Okay, I am going to go over the concepts a little more. And I was going to do some math today. I'm not going to. We're going to review what the math looks like, and we are going to do the math on Monday. So the first thing I'm going to have you do is print out this cheat sheet. If you can't print it out, you'll probably have to write it out, but you can use this on all your tests. You would be able to even if you were in my class. We learned about Boyle's law right here. We learned about Charles' law. We learned about Gay-Lussac's law. And then we talked about moles and volume, and this can be flipped, so moles are on top and volume on the bottom either way, and that's Avogadro's law. And these are the equations we're going to use, but we don't have to memorize all of them. All we have to do is memorize this combined gas law right here, okay? And how do we know which one of these formulas to use? We're going to use this handy dandy little box that I've created, and you'll understand that when we use it. But today I just want you to focus on the concepts, and then you're going to do an ed puzzle that goes over more of these equations and really how the math equations get set up. Okay, and then the last thing we have to do is learn about the ideal gas law. This is another equation. Notice there's not a 1 and 2 on here because there's not changing conditions. The ideal gas law is used when there's only one condition. And when we fill out this chart, if we have initial and final conditions written down, we'll use this combined gas law. But if we only have information on just an initial condition, we'll use the ideal gas law, and that'll go over one condition. That'll be a whole separate lesson. But these are the formulas that we are going to use. Okay, so let's talk about the concepts. Atmospheric pressure. This is the reason that some things get squished. But why do, for instance, an empty bottle not get squished from the atmospheric pressure? Remember, that's all these little guys bouncing around on the outside of the balloon, And then this balloon's staying in the same shape because the pressure on the inside of the balloon here is equal and opposite. So the balloon keeps its shape and it doesn't collapse. However, if we increase this external pressure, the atmospheric pressure, we would squish the balloon and the volume would go down. Okay, next we have the bell jar. We saw this video. We have a balloon here, and here we have lots of gas around there, and so the balloon isn't very large. But in this vacuum chamber, we pumped out all the air. So look, we only have 2 particles in here now. There's not a lot of pressure bumping in the outside of the balloon, so the pressure inside the balloon pushes out until the pressure inside equals the pressure outside, and that's why the balloon expanded, okay? When we have all these guys in here, we must have the same amount of pressure pushing out. When we removed it, the pressure inside this little balloon increased, so then the volume expanded in the balloon until the pressure inside the balloon equaled the pressure outside of the balloon. So Charles' law talks about volume and temperature. Here I have 3 balloons and they increased in size. Why did they increase in size? Well, you can see my temperature increased in each balloon. That made the particles inside the balloon move faster. We had more collisions. We had more pressure inside this balloon. So it had to increase to lower that pressure inside the balloon until it equaled the atmospheric pressure outside. The other thing I want you to notice is this is 100 K and it's 1 liter. I double the temperature to 200 Kelvin and I double the volume. Direct relationship. I triple the pressure to 300 K and I get 3 liters. So if we double the pressure, the volume, or I'm sorry, if we double the temperature, the volume doubles. If we triple the temperature, the volume triples. Now what's really interesting, and Avogadro came up with this hypothesis, it doesn't matter what kind of gas we have. If we have 1 mole of gas, it's going to be 22.4 liters. That's the constant at standard temperature and pressure. Notice helium, that molecule is a lot smaller than ammonia, so some people would think that the ammonia would take up more volume, but these are so tiny. Remember, one of our postulates is that our volume is 0. We don't even count the volume, it's so small. So the difference in size of these particles don't matter. 1 mole of any gas, it doesn't matter what gas it is, 1 mole is 22.4 liters, okay? Now, if I double the number of moles to 2 moles, guess what happens to my volume? It doubles to 44.8 liters. If I triple it, my volume will triple. This is our direct relationship. Volume and pressure are the only ones that are inverse, and that's Boyle's law. Okay, so the last thing I want to go over with you is this imploding can. Here's a fun experiment you can do at home. Instead of using a hot plate, you can do this right over your stove, and I would recommend that you put ice in this bowl full of water. This is going to explain air pressure inside and outside of a can with changing temperature, and they do a really nice job.
Hey guys, my name is Angela and I'm here with Savon and Priyanka, and today we're going to show you a fun, simple experiment that can be done all at home.
You will need an empty soda can, a hot plate or a stove, 1 large glass bowl of cold water, and tongs.
Kids, make sure you have a parent supervising you.
Now the purpose of this experiment is to show how a change in temperature can affect air pressure.
We're going to start off by filling a bowl halfway with cold water, which has already been done.
Now, with an empty soda can, add 1 tablespoon of
Just so you know, the change in temperature affects the pressure on the inside of the can, not the air pressure.
water to it. Make sure that the entire bottom of the can is covered.
Next, you'll be heating an aluminum can using a hot plate. If you don't have a hot plate, you can also use a stove. Please be sure to be very, very careful during this step.
Alright, make sure your hot plate is plugged in and turn it up to 150 degrees Celsius.
The water in the can should now be boiling. When the temperature increases, the water molecules in the can gain energy and turn into water vapor. You should see steam rising from the top of the can.
When this happens, we had a certain amount of air in there. Because the temperature goes up, a lot of molecules are escaping out of the top. So now we have less molecules inside the can. But the pressure is the same. You can tell because the can's not getting crushed. The pressure inside the can is the same, even though there's less molecules, because they're moving faster and they're pushing harder on the outside of the can, i.e. there's more collisions inside that can now, even though there's fewer molecules because they're moving faster.
Let it boil for 30 seconds. Now here comes the hard part. You're going to take your tongs and you're going to grab the bottom of the can. It's really important to make sure that you get a good grip on the can, like this. Now you're going to turn it upside down and dunk it into your cold water immediately, all at the same time.
Make sure you do this in one swift movement.
What happened? The can got crushed. When the water in the can was heated up, it turned into water vapor, and the water vapor was released from the opening of the can.
As a result, less molecules were in the can to maintain equal pressure inside and outside the can. When we flipped the can into the cold water, the drop in temperature caused the water vapor to condense back into liquid form. With less gas molecules pushing against the inside wall of the can, the pressure inside decreased. The atmospheric pressure became greater than the pressure inside the can, and as a result, the air molecules outside the can pushed the can inwards, crushing it.
Okay, let's review one more time what happened in that can. Well, first of all, we heated up the can, and when we did that, some of the particles left the can. The can, however, did not get crushed because these particles, what were left in there, sped up. And the collisions on the inside of the can were the same as the collisions on the outside of the can, or in other words, the pressure inside the can was the same as the pressure outside the can. When we turned it upside down in water, this was ice, it cooled these molecules, and these molecules slowed down, creating less collisions inside, which means it was less pressure. The outside pressure was now more than the inside pressure, and the can imploded or got crushed. So give that a shot at home. It's super fun.